So welcome, Michelle and Ashley and Eduardo and Evan and Lazaro and Ralph and Caesar and Victor and Nikki and Jacob and Bradley. Thanks for coming. The what we're going to start out with is the quiz as always. So let me share the desktop and we'll play around with the quiz.
How are you this morning, Larry?
I'm doing fine. I'm doing fine. Okay, so what we've got going on is we want to determine if the following series converge or diverge. That shouldn't be any surprise, by the way, because that's pretty much what, have you noticed, like most quizzes have been for the last couple weeks. So just let you know, this is the last quiz where that's all we're doing is deciding if something converges or diverges. After today, we're going to start using this stuff. Okay. Okay, or actually today I start using it, just not on the quiz. After the quiz, we use it. And be sure to state the theorems you're using. And the first one is a summation n equals 1 to infinity of n squared 3 to the n over n factorial. Okay, this particular one, you can go through all the different tests for convergence, and there's really only one that's going to work. What test should we try using?
The ratio test?
Yeah, ratio test. It's your only hope. And I'm just going to go through because I think it's always good to review the other tests, especially since we're at the end of the set of tests lectures to do. And notice that it's clearly, hopefully to all of you, not a geometric series. It does have a 3 to the n, but it also has an n squared of n factorial. Just to let you know, if you kind of visually take a limit as n goes to infinity, I don't know if you realize, but n factorial is gigantic. Okay, that dominates everything else. So that's going to destroy the n squared and destroy the n, and this is going to go to 0 as n goes to infinity. Okay, so the divergence test does not work. Is that clear?
I heard this thing that some infinities are bigger than others. Is that a thing?
There is a way of organizing infinities. I'm not going to get into details, but for example, the integers are smaller than the real numbers. Okay, but the real numbers, the number of real numbers is the same as the number in R2. But I'm not going to get involved in that. That you need to be a math major to get that.
Okay.
But I was, so I can, you can talk to me in office hours and I can chat more if you want. But we're not doing that in calculus. All we're doing is noticing that if we look at this, that the dominant term is n factorial, so divergence test does not work. Okay, you could try a comparison test. There's nothing obvious to compare this to. There's just too much going on. Do you agree?
Yeah.
Okay, there would be a way to compare. I'm just not going to go there. It would be a disaster. It's not a good step for comparison test. Okay, so on the other hand, this is just tailor-made for the ratio test because, as I mentioned, if you see a factorial, I'd say over 99% of the time, the ratio test is the way to go because factorials are really nice when you take an plus 1 over an. So we're going to use the ratio test. Okay, so let's go ahead and pop that in. And I'm just going to write limit. If I write limit and don't write anything else, that means n goes to infinity. And then we're going to have a ratio. And as I mentioned last time, it's an plus 1 over an, which is the same thing as an plus 1 times the reciprocal of an. And it's a lot easier to think of it as an plus 1 times the reciprocal of an. Hopefully you all know your fraction arithmetic and I don't have to explain why that's true. So if we do our an plus 1, that's n plus 1 squared. And let's make this fraction. N plus 1 squared. And then we have a 3 to the n plus 1. So everywhere you see an n, you put an n plus 1 times 3 to the n plus 1 over n plus 1 factorial. And then we're going to multiply it by the reciprocal of an. And that's going to be the fraction n squared times 3 to the n divided by n factorial. Oh, sorry, I didn't do the reciprocal. I said it and I didn't do it. Let's. So now I'm going to do the reciprocal and put the n factorial. Any questions? Any questions on this little arithmetic, this little ratio test use? Okay, so now that I've done that, I don't know if you remember, but what I mentioned, let me insert the equation. What I mentioned is what you do is we reorganize. Uh-oh. There we go. So I'm going to reorganize, and I'm going to put the factorials together, the powers to the kind of geometric theory part together, and then the polynomial part together. Okay, and that's how you always want to do these. So what I can think about is I'm going to have one more fraction, and I don't know, I'll put the factorial as the last fraction. We have n factorial over n plus 1 factorial. So let's get rid of that n factorial. Sort of moving around. Get rid of that n plus 1 factorial. And then the middle one, I'll just say n plus 1 squared. Over n squared. So get rid of that one. And then I'm going to take the 3 to the n and move that over to the left. Any questions about the rearranging? Any questions? Okay, that a rearranging really makes a difference in terms of making this doable. Okay, now what we can do is we can do some canceling. That was the whole point of rearranging. Oops, not what I want. That one. So what is 3 to the n plus 1 over 3 to the n?
3 to the power 1.
Yeah, or how about just 3? You could say 3 to the 1, but 3 is a lot easier to say. That turns into 3. Okay. N plus 1 squared over n squared. We can rewrite that. I can FOIL it out as n squared plus 2n plus 1. And what is n factorial over n plus 1 factorial?
1 over
over
n
n.
plus 1.
Yeah, it's 1 over n plus 1. So that becomes a 1. And then the denominator becomes an n plus 1. Any questions on that? Okay, well, now we're in good shape because look at the numerator and look at the denominator. Now they're polynomials. So notice that with these polynomials, the bottom, the denominator is a cubic and the numerator is a quadratic. So now what I can do is I can divide by n cubed. So let's do that. The 3 doesn't matter, it's just going to hang out. If I divide by n cubed, okay, then what I get in terms of top and bottom is this n squared becomes 1 over n. The 2n becomes 2 over n squared. And the 1 becomes 1 over n cubed. And then what I can say is when I divide by n cubed, the n squared actually goes away. And the n plus 1 becomes a 1 plus 1 over n. Any questions so far? Okay, now what happens when n goes to infinity? What happens to the numerator?
Goes to 0.
Goes to 0, and what happens to the denominator?
It's 1.
1. So what, I hope you all know, what is 0 divided by 1? Times 3.
0.
0.
Okay, so that's the important thing. And what's important about the number 0 for the test we're using, for the ratio test? What's the key thing about about 0? There's a whole, we're at the punchline.
It's less than 1.
Exactly. Because with the ratio test, you're comparing with 1. So therefore, by the ratio test, the series converges. Any questions at all about the first series test? Any questions? Okay, let's do the second one then. Okay, the second one, we have a summation of 4n plus 7 over 7n plus 4 to the n. Okay, and you could look at all the different tests. This is not a geometric series. The limit is even hard to look at. If you tried to imagine what the limit is and goes to infinity, that's just going to be a mess. There's nothing to compare it to. It doesn't look like anything. The ratio test would not be happy at all. What test can we use?
Root test.
A root test. I want to give you a warning though. The biggest difference between the quizzes and the exam is that the quizzes you usually only have 1 or 2 tests to think about. And you know it's going to be one of those because that's how I test. For the exams, I'm just going to say, decide if it converges, and you have to know what test to use. So you should always go through the test to see which one works. Okay, instead of just say, oh, well, we're at the root test day, because when you get to the exam, that won't work. So we use root test, and this is just set up for the root test because everything is to an nth power. So if we take an nth root, I'm just going to write it in words. The nth root of an is 4n plus 7 over 7n plus 4. Everyone good with that? Any questions at all on that so far? So we've taken the nth root, and now what are we supposed to take?
The limit as n approaches infinity.
Yeah. So now take the limit as n approaches infinity. And there's actually 2 ways. I think L'Hopital's rule is the easiest because I can, in my sleep, take the derivative of 4n plus 7 and get 4, and 7n plus 4 and get 7. Notice that, by the way, when n goes to infinity, you get infinity over infinity. So L'Hopital's rule applies. So you get 4 over 7. What's important about the number 4 over 7?
It's less than
It's
1.
less than 1.
It's less than 1. Therefore, what can we say about the series? by the root test, D series converges. Good. And that's the quiz. Any questions at all? Any questions at all about A or B for this quiz? Okay, I do want to remind you, I take off points if you don't specifically state the test you're using. The root test in this case, maybe I'll even capitalize it to make it louder. And the ratio test in the first example, first question. So if you don't state the test you're using, then you lose points, because that's kind of the purpose of this is to give your rationale, and your rationale is the citing the theorems. Any questions at all about the quiz? All right, I have a question for you, actually a vote. And you can vote in the chat box if you want. And that is the quiz for what we're going to talk about today. We have two choices. You can have it on Friday, or you can have it on Monday. And we'll take a vote. So vote Friday or Monday. So the idea is, remember, Friday is your presentation day. So do you want it, before the presentations? Or do you want to have kind of a short Friday? We'll do the presentation, be over, and then have it on Monday. So type in the chat box whether you want Friday or Monday. I'll let you choose as a group, of course. Okay, it's not unanimous, but it's pretty close to unanimous. So sorry if you said Friday, but I'm seeing a lot of Mondays. So we'll have the quiz on Monday. Okay, so Friday might be a short day, by the way. I do want to just mention briefly, maybe I'll even move on to this guy. Mention briefly about Friday. So Friday, again, there won't be a quiz, so make sure you absolutely log in at the beginning of the time. And the way it's going to work is you're going to, one group at a time, and I'll let you volunteer on who wants to go first or not. If nobody volunteers, I'll volunteer someone, by the way, but it's always better to volunteer, and who wants to go second, third, etc. And remember, you have to have 2 or 3 in your group, so you better all have a group. Okay, and I'm here to help you too. A lot of people have been asking in office hours, emailing me, and I'm happy to help. So again, this is not a test, it's a presentation. So the way it's going to work is I'll just start out by saying hello, basically. And then a couple things. Then the first group will go. And I'm going to let you choose. If anyone in the group doesn't want to be recorded, I can pause the recording. But you have to let me know to pause the recording. On the other hand, if you're okay with it being recorded, then I'll record it. Okay? It does get put on YouTube. And I don't know if you all realize, but I have over 1 million views already. So, it is public. So if you don't want to be public, then you can say no. But honestly, nothing is going to happen to you because you gave a 5-minute presentation on a application of calculus. Okay, even if you run for president someday, they're not going to like zap you because of the calculus application you did. Okay, just let you know that. Okay, so, but if you don't feel comfortable, anyone has a veto power, and then I hit pause recording, and then it doesn't record you. And then I'll re-record, I'll start the recording again when it's for the next group that is okay with it. So just a note, because again, I don't want to force you, I'm not even allowed to force you to be public, okay? That's why I like these votes and stuff, I say do in the chat box, because the chat box is not public. Okay. So what's going to happen is you're going to give a 5-minute presentation. You should go the full 5 minutes, okay? And then after that, it's going to be open up for questions. Okay, so it'll take up to maybe 10 minutes or so, possibly, depending on how many questions there are. And if the questions go forever, I'll stop them, but I doubt they will. There'll probably be a question or two, and I might ask a question too. Okay, so be ready to answer questions if you can. You know, do your best. And then that'll be over. And then the next group will come in and we'll keep going until we're done. And again, I think there's 18 in the class. So if there's an average of what, 2.5 or so per group, then we're talking about 7 or 8 different presentations. If each takes 5 plus Q&A, that is going to be a little over an hour. Okay, so that's the plan. Any questions about how the presentations are going to be going? And what I'm going to do is I'm going to award points as a few homework assignments and put it under that category because it's a 1-day thing. It's a 5-minute thing. It's not an hour test. But it's more than a homework. So I can't force you to stay, but it's nicer to your classmates if you stick around when you finish. Okay, because that way you're listening to each other, you're supporting each other. Okay, if you have to go to work or something, then that's a whole different thing. But if you can stick around, that's better. Does that make sense? Okay, just like I don't force you to stay during my lecture either, but it is helpful. Okay, so, and it's more polite to stick around. Okay, any other questions? Any other questions? Okay, if there's no questions, I think it's time to go to do some math. And I want to revisit the geometric series. So the first thing is, who remembers what a geometric series is? It's been a little while since we've played around with them. Who remembers the geometric series? What do they look like? What's a geometric series look like?
It's something to the power of n, right? Or it's like some number to the power of n?
Yeah.
Okay.
Okay, so geometric series is exactly, it's something to the power of n. And for now, I'm going to use what the book used originally. We're going to change that, but for now, we're going to do that. So, okay, and by the way, so let's write it out. Insert equation, and it's going to be a summation. And actually, this one, I'm trying to remember whether this had it. Oh yeah, this had this summation. That's better. So it's a summation, n equals 0. I like to start at 0, especially for today. N equals 0 to infinity, and that is important that it's infinity. And you can have a first term, but I'm just going to leave that out because you can always pull the first term outside the sum. So I'm going to look at it as some constant p to the m power. Okay, so that is the geometric series. And again, there could be a constant in front of it. Could be a naught times p to the n, and you can always pull the a naught out. So it's not that exciting. Okay, so that's the geometric series. Now comes the next interesting part. And remember the formula. This was like the one series we actually were able to find out what it was when it converges. And who remembers the formula for the geometric series? And you remember? And it's been a little while, but it's only 2 weeks, I think. Okay, let's see y'all jumping in. Yeah, now notice the A1 or the A naught, I'm just letting it be. Yeah, R can't be 1. R can't be greater than 1 either, actually. Okay. So if you want to call it R, we can call it R instead of P. Doesn't matter what letter you use. Okay. And it looks like it's a little more complicated. So it's a little simpler than you're making it because it's going to infinity. And what this is 1 over 1 minus R. Want to make it bigger? Okay, that's a really, really, really important formula. And this only works, by the way, when the absolute value of R is less than 1. So again, this is a review, but I know how it is. Doesn't mean you remember it. Absolute value of R is less than 1. So you're right when you said R can't be 1, but it can't be 2 either. Okay, you get infinity, it just doesn't work. Any questions on that? Okay, now what is R? What does R represent?
The common factor.
Yeah, in particular, it's a number, right?
Yeah.
So now it's time to change things a little bit. Okay, and all I'm going to do, I'm going to copy and paste this. And I'm going to take that R. I'm going to change the letter. Technically, that doesn't do anything. But realistically, it changes everything. Because now when you see something like that, given the fact that you have been ingrained to think of X differently than R, now what does it feel like when you look at 1 over 1 minus X?
It feels like we can solve for X.
You can solve for X, but in particular, you could do things like graph it, right?
Oh yeah.
It's a function. Is that clear? So by writing it this way, I can actually think of this as not just a series that gives you a number when you're done, but a function of X. Any questions on that? So now I've defined a function of X, which by the way is also 1 over 1 minus X, but you can write that as a series, summation n equals 0 to infinity of X to the n. Is that clear? And then when we say when X is less than 1, thinking about in function language, what's the language saying that X in absolute value is less than 1? What does that represent in one word?
A fraction.
No, absolute value of X is less than 1. One thing that's not a fraction. Remember? That's the domain. So the domain, so instead of when, I'm going to write with domain. Absolute value of X is less than 1. Because it's a function. When you have functions, you should always be thinking about domain and range in the rule, right? The domain is all values of X less than 1 in absolute value. The rule is n equals 0 to infinity of X to the n. And it's also equal to 1 over 1 minus X. Any questions on that? Okay, technically, this doesn't really work. Anyone see? It's a very technical issue, but it's one that you know that you've seen before in your life. Not this quarter, by the way. Anyone see it? Okay, it's subtle, so I didn't expect anyone to see it, but I figured maybe I'd get lucky. And the idea here is that there's a problem with X equals 0. What's the problem with X equals 0?
You get 1.
No, you don't get 1. It's a problem. The problem is you don't get 1. You don't get anything. Why don't you get anything? This you got first quarter calculus. What is 0 to the 0 power?
Undefined.
Yeah, undefined. Okay, so technically this be undefined, but I'm going to write this out in words for the rest of the quarter. When you see a series, a function as a series, we will define 0 to the 0 to be equal to 1. Okay, I know that's not true in all of the math, but just for series, when you have a summation with an x to the n, and you end up with that first term being 0 to the 0, we're going to call that 1. Okay, if you had to do it like right, then what you would do is you write it as a piecewise defined function, but no one does that. They just say, well, we're just going to let that, whenever you see that and you're plugging in the 0 with n equals 0, just call that 1. Sound fair? Okay, so it saves a lot of work not to have to like do the detail every time. So that's just going to be the convention for these guys, for these series. Any questions on that? Okay, so this is, I like to think of this as kind of the easiest non-trivial example where we have a summation and involves x's. All right, now it's time to get into the big general definition, and this is really important. This is called this is a definition. And that is, I can copy and paste and change. If you have a summation of a sub n times x minus c to the n, and I'm going to even write that as f of x is called a power series centered at x equals c. Okay, so we look at this, summation n equals 0 to infinity, an x minus c to the n, and notice this is a function, because if you give me a value of x, then there's a number, okay? Or there may not be a number. If there's not a number, then it's not in the domain, and that's okay, it's still a function, right? So it's a function. So the name we use for these functions that are written in this way are power series. Any questions? Any questions on this big definition? This is what we're going to be doing for the rest of this class, by the way. That's all we're going to do is we're going to do power series. So this is a very, very deep and very, very important topic. So just to let you know, and we'll be doing this in, I think that's Wednesday, is that every nice function can be written as a power series. So what this tells us is that we're able to rewrite every function that you're used to, basically, as a power series. Now, sometimes power series are easier to deal with, and sometimes they're harder to deal with. But the point is that whenever you have a function, then you have an option to take that function and think about it as a power series instead. Okay? Again, today we're not going to talk about how to do that unless it's the geometric series. Okay, so if you have 1 over 1 minus x, then you can rewrite that as a power series. Okay, well, it turns out you could do the same thing for sine of x or e to the x or, I don't know, natural log of x plus 7 or most functions that you can think of, as long as they're nice, and in calculus, nice means you can take lots of derivatives, then it turns out that every function that's nice can be written as a power series. And power series have some very good properties. Those properties we'll be talking about on Monday. Okay, remember Friday you guys talk, but Monday I'll be talking about some really nice properties of power series that takes everything you did in calculus and makes it trivial. Okay, but there's issues with power series too, just a warning. So this isn't quite the end all of all math, but what it does is it allows us to do some things, and especially by computers. So I'll let you know what you typically do in terms of the real world is you take a function, turn it into a power series, and then take the infinity and make it big, like instead of infinity, make it maybe 1,000,000. Let a computer do it, and then you've got it. So even if you started with a really miserable function, a computer can handle it, okay, even if we can't. And that's the whole purpose of these power series. This is a major, major, major definition. So let you know that there's whole courses just on working with power series. And for example, let me give you an application that's very difficult, by the way. But you've probably heard of like the Schrodinger equation, right? And you've probably heard of solving the Schrodinger equation basically for the hydrogen atom. Have you heard of that in chemistry or physics? I'm sure you haven't seen the solution, but you've probably heard of it, right?
Yeah.
Okay, well, if you jump up from hydrogen to anything else, okay, and there's a lot of other elements out there, helium or oxygen or nitrogen or whatever, and you look at the Schrodinger equation, it can't be solved. So what they do is they turn it into a power series, and then you can approximate it to as many decimals as you want. And that's how it's done. Okay, that's how all of that stuff is done. Okay, and we'll see some examples. We won't see, the example of doing nitrogen or something. That's beyond this class. But I will let you know that these power series are really important for complex equations that you need to solve, and particularly differential equations. Okay, and do you remember I said that last quarter? I don't know if you remember, but can you integrate every function?
No.
Right? If you have a differential function, for example, can you integrate it?
Yes.
You can? Do you know how?
No.
Okay, so here's the deal. Within the next 2 weeks, the answer is yes. Okay, but you're going to have to do power series. So just let you know that all the stuff that you otherwise can't do, now we'll be able to do them with power series. This is a very, very important topic that comes up in a very big way for difficult problems. Doesn't come up for easy problems, but it comes up for difficult problems. Any questions at all on this big definition? Okay, it's easy to come up with examples. The geometric series is an example. Maybe I'll just write some more down. Not there's much to say about it, but just for fun. So let's suppose we have the summation. That one, yep. N equals 0 to infinity. of, how about x to the n? Oh, wait, I need to make a fraction. X to the n over n factorial. Make that a little bigger. Is that a power series? Is that a power series?
Yes.
Yeah, it's a power series. Okay, in this case, a sub n is 1 over n factorial. What's the center of this power series? Where's it centered at? Hint is it's easy. Yeah, it's centered at 0, because you can think of x as x minus 0. And in fact, I'd say 3/4 of all power series you ever see will be centered at 0. Because if it's not centered at 0, you can always do a translation and make it centered at 0. So most of the examples I'll give you are centered at 0, but there's sometimes it's easier not to center at 0. Okay. Just to let you know, and we'll prove this another day, not today. Does this look familiar, this power series? Like, do you know what function this is? Any guesses? Okay. I guess you probably don't, but I will let you know this is just a power series. This is the most important set power series in the universe. Okay, by far. It's e to the x. Okay, again, that's not today. Today we're not going to see why this is the same thing as e to the x, but this is e to the x. Okay, so what the whole point is, we can take a function like e to the x, and we're going to be able to write a power series to replace that function. And then we could look at it in a different light. Okay, I know e to the x is a simpler way of writing things, but there's some things that are easier to do with power series than to do with e to the x. Okay, I promise you. And we'll do that another day. So this is an example. Let me write example. And that is the big e to the x power series. Any questions on that? Okay, so now one of the things you want to do, since we have this big definition and there's a power series, and you want to think about the function, we're concerned with what is the domain of the function. The typical thing you do when you're doing beginning or intermediate algebra, right? When you're just starting with functions, you're asked to find the domain, right? So what is another way? So let's see if you can tell me. Of wording the sentence. What is the domain of this power series function?
My guess is, does it converge or diverge?
Close, but your wording is a little off. But you got the converge or diverge, right? Kind of. But not does it. Because remember, if I say find the domain, you're not going to say yes. Right? The domain isn't a yes or no question. And does it converge or diverge is a yes or no question. Does that make sense?
Yeah.
So what we want to do is want to say, well, how can we think about this as something about converge or diverge with the domain? Okay, if you can't think about it, let me explain. And that is the answer is for what values of x does the series converge? Any questions on that? Because when you're asked to say what is a domain, that's the same thing as what values of x can you plug in and get a number. And asking, does the series converge, is equivalent to saying, do you get a number? Do you see that? And being in the domain means you get a number. Not being in the domain means you don't get a number. Is that clear? Any questions on that? Okay, so finding out what the domain of a function is very important. And we know how to do it because we spent the last 2 weeks learning how to do that. So as I mentioned, what we've been doing, what we did in the last chapter, is absolutely essential to be able to understand what we're going to be doing in this chapter, because we have to understand what the domain is. Okay, on the other hand, what we did in the first 6 weeks of class is completely unrelated to what we're doing now, just to let you know that. Okay, we're not touching any of that stuff. Okay, there can be relationships, but not in this class. Something I'm not going to do in this class, because it's upper division math, is you could, instead of looking at f of x, you could do f of x comma y, and you could do a 2-variable power series. We're not going to touch it. My guess is most of you will never see that in your life because it's advanced. So for us, the first half of the class and the second half are completely separated, but the chapter on sequences and series and the chapter on power series are completely related. Okay, so now, and this is just language coming up. When we're talking about power series, we tend to use different language. We don't use the word domain. So let me give you a definition for some of that language. So the definition is as follows. Let f of x, copy it in so I don't have to keep writing it. Let f of x equal this power series. Then the interval of convergence is the domain of f of x. Any questions on this definition? All right, so just reading the words interval of convergence, it kind of suggests something. What's it going to suggest?
We're bounded.
We're bounded. It's definitely bounded, but it's actually stronger than that. Okay, the answer is very obvious. All right, if I don't hear it, the domain of a power series is always an interval. Okay, so that's a theorem. Let's write it out. And even writing it out, it doesn't feel like it's saying anything, but it really is pretty deep. The interval of convergence is an interval, which is the same thing as saying the domain of any power series function is an interval. Now it could be the trivial interval. For example, notice that if x equals c, then it always converges. How come? Let me write that down. Note that the power series always converge at their center. Why is that true? Yeah, I think
Because their center is a number.
Yeah, but off the center is still a number. Right, the center is 5 and you plug in 7, 7's a number too. But it's very important to look at. It should be obvious when you look at the equation, when you look at the definition equation. What happens if you plug in c for x?
You get a sub n.
Not a sub n, but you get a sub 0. Okay, then you always get a sub 0. And that's it. So that converges. A sub 0, and then all the rest emerges zeros. Does that make sense? Because 0 to the first is 0, 0 to the second is 0, 0 to the third is 0. Just always get 0, except for the first one. Remember, 0 to the 0, we're calling 1. So power series always converge at their center. And then the question is, where else do they converge? And it's going to be an interval. And let me finish the theorem and add more. Centered at C. Any questions on the theorem and the note? All right, so why is the theorem true? That's the next question, is why is it always an interval? And the idea is what we have to show is that if it converges at a value away from the center, then it converges at every value closer to the center. Does that make sense? So let the series converge at, let's say, x equals b. Does that make sense? Okay, and let's say b is not equal to c. There it is. So let's say it converges at a value that isn't the center. All right, well, we want to look at, so that means that if we take this series and we plug in x equals b, it converges. Is it a little too big? Okay, that's what it means to converge at x equals b. What happens if we get closer to c? So if we pick a value closer to c than b, then what we can say is that b minus c to the n will be greater than that closer. So a value, I need to give it a letter. I don't know, t maybe. Will be greater than t minus c to the n. At least in absolute value. Any questions on that? Because remember that the absolute value of b minus c is the distance from b to c. The absolute value of t minus c is the distance from t to c. If t is closer, then the b minus c to the n must be bigger than t minus c to the n in absolute value. Anyone lost on that idea? All right, well, we want to find out if this new series converges. Now it's time to think about the last chapter. What test can we use? If we have something that's bigger that converges, and we want to find out if our original thing converged, what test can we use? And by the way, you can throw in an AN if you want, just for fun. Because that doesn't change anything if you multiply both by AN, just to make it really look right. Yeah, this is a comparison test. So therefore, or by, there we go. By the comparison test, I'll write CT, the series with the T. Converges. Okay, so that's a proof that the points of convergence, or the domain of the function is another way, the interval convergence really is an interval. Because once you know it converges at a value, then everything closer to C from that value also converges. Any questions on that? In absolute value, so it's both directions. So that tells you C is a center. Any questions at all on this? Okay. There's another definition. So if you have an interval with a center C, then we can think about the distance from C to the end of the interval. From the center C to the end of the interval, and either end because C is in the middle, of convergence is called the radius of convergence. Let's make that in red. Okay, when you think of radius, what do you think of, by the way?
Circles.
Circles. So I want to give you a warning. These are intervals, not circles, right? Any guess on why we still call it the radius of convergence? Any guess? You can think of circles. You could also think of as spheres, by the way.
Is it because we eventually use it for multivariable stuff?
Exactly. Exactly. So that, and we as in, it won't be we, because I won't be your professor for that if you decide to take the advanced math. But when you get into multivariable, so for example, when you do the true Schrodinger equation, then you're not talking one dimension, you're talking 3 dimensions typically. And then you got to do multivariable. So if you're doing the multivariable stuff, then you need to handle this radius of convergence idea. Okay, and then it really is a circle or a sphere, or you can go higher than that in dimensions. Okay, so just let you know, there's a reason why it's not just to be tricky that I'm calling it radius of convergence. It's because you want to be able to expand to higher dimensions. But in our class, we're not going to expand. We're going to stick to just one variable. Any questions on this definition? Okay, so an interval is defined, there's different kinds of intervals. So see if you can tell me, what is the difference between, say, -1, 1, -1, 1, -1, 1, and -1, 1. Okay, the way you say them is all the same, but notice the first one has parentheses around both. The second one has a square bracket around the left and a parenthesis around the right. And the next one, parenthesis on the left, square on the right. And then the final is bracket, bracket. So what's the difference between them? So what does it mean? See if you can remember your very basic math.
So the first one in parentheses means it's not completely bounded there. The second one, it stops indefinitely at -1, but not necessarily at +1. Same as the third one. It's not specifically bounded at -1, but it is definitely bounded at 1. And then completely bounded at -1, 1 on the last.
Okay, your ideas are all right. Your vocabulary is not perfect though.
No,
You don't want to use the word bounded, you want to use contains.
contains. Okay.
Yeah, or includes is another word. Contains or includes. So does it include the left and right endpoint or does it not? Does that make sense?
Oh, yeah.
Okay, so let me give you, this is step-by-step process of finding the interval of convergence. And step 1 is use the ratio test. Capitalize it. To find the radius of convergence. Step 2. Step 2 is use another test to consider the left endpoint. And then step 3, I'm going to copy and paste it because it's almost the same. Use another test to consider the right endpoint. So that's going to be the step-by-step process on finding the interval of convergence. So let's do an example. Let's consider, so let's say find the interval of convergence of the sum n equals 0 to infinity of what x minus 2 to the n over n plus 1. make that a little bigger since it's an example. Any questions on the question? Okay, so what do we do? First thing we should do?
Find out where it converges.
Well, that's everything we have to do. But the first step in that,
Do the ratio test.
yeah, we find the ratio test, or we use the ratio test. Let's use the ratio test. So let's go and do that. We're going to take a limit, and then we do ratio. And hopefully you're used to this. I told you ratio test is important, and this is the reason why it's important. Because a main thing we need to be able to do is find interval of convergence. That's the number one usefulness in convergence tests. So what we're going to do is x minus 2 to the n plus 1 over x minus 2 to the n hopefully you're okay to, I'm going to kind of do two steps at once. And then n plus 2, n plus 1 over n plus 2. Any questions on that so far? Okay, oh, by the way, something I need to do, and this is important. The ratio test involves absolute values. Any questions on that?
So how did you get x minus 2 to the n in the denominator of your first fraction?
Because remember, you multiply by the reciprocal.
Okay, so you just combined them after doing that?
Yeah, I kind of did two steps at once because
I
I only have
see
so
it.
much time.
Thank you.
So I did the two steps. Okay, but I promise nothing too advanced. Okay, we need that limit. Look at the numerator. I'm sorry, not the numerator. Look at that first. X minus 2 to the n plus 1 over x minus 2 to the n. That simplifies very nicely. How does that simplify?
X minus 2.
Yeah, in absolute values though. So that is going to be equal to the absolute value of x minus 2. Okay, what about n plus 1 over n plus 2? We're taking a limit that then goes to infinity. That you should all be able to do from first quarter calculus. Very basic.
It's 1.
Yeah, it's just 1. So now the ratio test says this needs to be less than 0 and less than 1. Any questions on that? Okay, so now we got to go back to your beginning algebra, and you got to remember how to solve absolute value inequalities. What does that tell you? So what must x be? And remember how to do that? You set them equal, x minus 2 equals 1. By the way, if x minus 2 equals 1, what do you get? Should be able to do that in your head, hopefully.
3.
3. And then you also go x minus 2 equals negative 1. Do you remember that's how you do absolute value inequalities? And what do you get for x?
Negative 1.
X minus negative 1 minus 2 is not negative 1. So x minus 2 is negative 1 is 1. 1 minus 2 is negative 1. So that tells you negative 1 is less than x is less than 3. Any questions on that? Okay. Note, by the way, if x equals 3, then the absolute value is 1. And do you remember what happens with the ratio test if the absolute value is 1? If you get 1 for the limit?
Doesn't
Or the
work.
ratio? Yeah, it doesn't work. Okay, that is the reason why we have to do step 2 and step 3. Because the left and right endpoints will never work with the ratio test. Because the left and right endpoints will always give you 1, which means that it didn't work. Does that make sense? So that's why you have to use another test. So now we have to try -1. So now let me write down 1. That was step 1. Now let's go to step 2. Okay. So for step 2, we plug in -1. I don't know if I said left or right. Doesn't matter which one you do first. Let's see, left first is what I said. So if you plug in -1 into the series, let's go back up and look at the series, then this just becomes -1. I'm sorry, if you plug in, no, it wasn't -1, it was 1, sorry. Much better. I knew something was wrong. So if you plug in 1 into the series, then we look at this, and this is going to be very common. What's 1 minus 2?
-1.
-1. And we get -1 to the n plus 1. So actually, let's copy and paste. It's faster. And that x minus 2 becomes a -1 to the n. Okay, and we got to test this for convergence. All right, what test are we going to use for this one?
Alternating series test.
Yeah, so by the alternating series test, this series converges. Any questions on that? Okay, so now we know that 1 is included in the interval of convergence. -1 is, 1 is included in the interval of convergence. Okay, what happens when we plug in 3? So let's go back to our series. If we plug in 3, what does the numerator become?
+1.
Yeah, it just says 1. 1 to the n is just 1. So now what we can do is go to step 3. And take that numerator, turn that into a 1. And what test can we use now?
Comparison test.
The comparison, or notice this is the harmonic series. Do y'all realize that? I know you're used to seeing a 1 over n, but if it starts at 0, it's 1 over n plus 1. That's the harmonic series. So by the harmonic series test, this series does what?
Diverges.
Diverges. Any questions on that? Okay, therefore, the interval of convergence. Well, we know it's between 1 and 3, but we know it includes 1 and doesn't include 3. And that's the answer. Any questions on this example? Any questions? Okay, so the nice thing is we're going to be reviewing the last chapter a lot when we're finding out what the interval of convergence is. All right, so let me give you the next example, which is different. Write out the power series for, does that work? Yeah. The summation, oh, sorry, no, I don't want that. Insert f of x. F of x equals four over 2 minus, let's say 2 plus x squared. Well, how do you do it? What does this look like? And the hint is, it's the only function, there's only one function you know how to find a power series for. Yeah, geometric series. All right, what's in the way?
The x squared.
The x squared and also the 4 and the 2. So we can rewrite this, and that's the key on this. As well, we can write this as 2 times the fraction 1 over 1 plus, actually 1 minus parentheses, and then we can say x over the square root of 2. That one, yeah. Square root of 2 squared. This is a little bit like when we did inverse trig integrals, where you have to kind of adjust, kind of massage the equation to make it look like what you want. Would the numerator still have a 2? Let's see. I pulled the 2 out. So I pulled a 4 over 2 out. So I pulled the 4 out on the numerator, and I pulled the 2 out in the denominator. Does that make sense? And 4 over 2 is 2. Is that okay? Okay. Now I can write this as a geometric series. Oops. So this is going to be equal to the sum. That one. N equals 0 to infinity. And in fact, I'm going to pull the 2 out completely. And what we get is x over root 2 to the n. Okay, is that clear? And we can rewrite that as root 2 1 over root 2 to the, so let's write this out. 1 over 2 to the n over 2 times x to the n. You know, I forgot one more negative because it's a minus. Let's see, the minus, one more negative here. There we go. The minus a minus. Looks a little weird, but that's the way it is. And then we're going to have a negative 1 to the n on the top. And there's our power choice. Okay, and that is an example where you have a function that's not exactly the geometric series, but you massage it a bit and you make it a geometric series. I don't have time, but other examples is sometimes you get to complete the square in the denominator to make it a geometric series, and then it'll be centered somewhere else. Any questions at all on this example? Okay, I'm going to stop the recording because we're out of time.